Welcome to the fourth tutorial. In this tutorial, our focus of attention is on concepts in main memory and address translation techniques. We have already covered in our lectures what is organization of main memory, and we have seen that main memory organization consists of channels, DIMMs, ranks, banks, rows and columns. Today we will have a couple of problems which will deal with about the address mapping techniques in main memory. So look at the first problem today. Consider a system that uses 24-bit virtual address space and 20-bit physical address space. It uses a paging scheme that employs 4 kilobyte pages. The page table for a program is indexed based on virtual page number, and each page table entry consists of the frame number and 8 control bits. What is the size of the page table in bytes? So, we have to find out what is the size of the page table. There are two things what we have to understand in this context. When you talk about a page table, there are the number of entries in the page table. That is depending on the number of pages in the program. The number of pages is dependent on the virtual address space. So, first you have to find out number of rows in the page table and each of the row how much of information is being saved. So, here it is mentioned that the page table for the program is indexed based on virtual page number, and each of the entry contains a frame number. It is not the address, it is a frame number and 8 control bits. So, first we have to find out number of rows, and in each of the row we have to store a frame number and we have to store 8 other control information which may be page replacement bits, other valid bit, dirty bit, etc. So, let us try to find out what are the number of bits required for representing a virtual page number. So, number of pages, that is defined as, you have 24-bit virtual address. So, 2 power 24 is the total virtual memory, divided by, it's divided into pages each of capacity 4 KB. So, 4 KB is 2 power 12. So, you have 2 power 12 meaning 12 bit page number. Now, number of frames, number of main memory frames, it is depending on the physical address. We have a 20-bit physical address, so it's 2 power 20 is the main memory capacity divided by number of page, the page size is 2 power 12. So, that you will get it as 2 power 8. So, meaning I have an 8-bit frame number. Now, if you look at your page table, the page table has n entries where n equal to number of pages. So, I have 2 power 12 pages. Now, it is an 8-bit frame number will be stored in each of the entry plus 8 control bits. So, each of the entry, each page table entry has an 8-bit frame number plus 8-bit control. So, this is frame number and this is control information. So, together I have 16 bits, or it is also known as 2 bytes. So, I have total of 2 power 12 pages. Into each of these pages is going to consume, each of this entry is going to consume 2 bytes. So, I have total of 2 power 13 bytes is needed for implementing the page table. It is also known as 8 kilobytes. So, the final answer is 8 kilobytes. Let us try to revisit what we have done. We have to find out the number of pages. Number of pages is obtained by total virtual memory space, that is 2 power 24 divided by what is the page size, that is 2 power 12. So, you get total 2 power 12 as the number of pages. So, it is a 12-bit page number. Now, we have to find out the number of frames in a similar fashion. What is the physical address? Physical address is 2 power 20 divided by page size, that is 2 power 12. So, we get 2 power 8 as the number of frames. So, to represent a frame number we require 8-bit. So, each of the page table entry has an 8-bit frame number plus an 8-bit control information, together 16 bits, that is 2 byte per page table entry. we have total of 2 power 12 entries in the page table. So, 2 power 12 into 2 bytes, that is 2 power 13, it is 8 kilobytes. Moving into the next problem, a 32 GB DRAM system uses 4 channels Z0, Z1, C2 and C3, and it has total of 4096 columns per row. It uses an 8 byte wide memory bus to transfer data from DRAM to the processor. If adjacent words are mapped to adjacent memory channels, which channel will fetch the physical address? So, let us try to divide the splitting. It is using a 32 GB DRAM. So, if it is a 32 GB DRAM, then it is basically 2 power 35. So, what I need is, I have 35 bits in the address. So, given the address, it is 35 bits and 8 byte was, so the last 3 bits will be byte within the bus. Now, this is what is called a word. So, one word consists of 8 bytes. So, once you transfer a word, then 8 bytes are getting transferred from the memory into the processor. Now, here it is mentioned that adjacent words are mapped into adjacent channels. So, once I transfer a word 8 bytes, the next 8 bytes are located in the next channel. So, we have 4 channels. So, the channel bits will be coming here. These are the 2 bits for channels, and then I have 12 bits, that is total of 4096, 12 bits for the column, and then followed by the row, bank and other things. So, these are the remaining bits. So, for me the channel bits comes just after the byte within the bus. So, the last 3 bits, the least significant 3 bits will be used for bus values. So, what we do is, we are going to take the next 2 bits. So, these 2 bits will tell you what is going to be the channel number. So, consider the address. So, out of which I will take only the last 4 2, that is only our interest. 4 stands for 0 1 0 0 and 2 stands for 0 0 1 0. Now, this much value is gone for byte within this bus, and these 2 will tell the channel number. So, 0 0 indicates channel 0. So, this particular address is coming from channel 0. So, I will try to re-summarize what we have done. Given a DRAM system consisting of 4 channels, and it is mentioned that we have adjacent words mapped into adjacent channels. So, one word corresponding to 8 bytes. So, the last 3 bit of the address is actually bytes within a word, and the next bits in the address, looking from the least significant side, they should be given to the channel. Then only adjacent words will be going into adjacent channels. So, when you take up the last 8 bits, here the value is 42. Once you write that, the last 3 bits will go to byte within this bus, and the next 2 bits is used for channel. Since the 2 bit value is 0 0, then it is corresponding to channel 0. If this 2 bit value could have been 0 1, then it is channel 1. If it is 1 0, then it is channel 2, and if it is 1 1, then it is channel 3. Now, we move on to the third problem. So, consider a 64 GB DRAM system organized as 4 channels, each channel with 2 DIMMs, each DIMM has 2 ranks. The system uses 8-bit chips and 8 banks. Each bank has a collection of byte cells and can store 8 bit of information organized as rows and columns. That is the meeting point of a row and column is a byte cell. The bank configuration is in such a way that the number of rows and columns per bank is equal. The system uses 8 byte wide memory bus to transfer data from DRAM to the controller. Each channel is connected to 16 gigabytes of continuous memory. So, let us try to look into the last line. Each channel is connected to 16 gigabyte of continuous memory. I have total of 64 GB, and that 64 GB is spread across 4 channels. Now, when you have 4 channels, and the peculiarity is that 16 GB of memory is continuous inside one channel. So, first 16 GB is channel 0, next 16 GB is channel 1, next 16 GB is channel 2 and the last 16 GB is channel 3. For this to realize, we have to dedicate the most significant 2 bits for channels. So, let us try to divide the split up of the address. So, once you take the address, we have total of 64 GB DRAM. So, 64 giga means 2 power 36, that means I have total of 36 bits in the address. Now, 2 bits is gone for channels and it is the most significant 2 bits are gone for the channel bits. And then we have 1 bit for the DIMM and then we have 1 bit for the rank. So, it is 1 bit DIMM and 1 bit rank because we have 2 DIMMs and 2 ranks. So, 1 bit is sufficient enough. And let us say we have now 3 banks. So, 3 bit banks. So, it is 8 banks are there. So, 3 bits are dedicated for banks and we have to understand that the number of chips that we use is no longer relevant as far as the splitting of the address is concerned. Since we use 8 byte wide memory bus, the last 3 bits, that is each of the word is corresponding to 8 bytes. So, the 3 bits are used to find out these 8 bytes. So, now if you look at the total is 36, out of which now 10 bits are used. You have 3 bits for bus, you have 3 bits for bank, this is for bank and then you have 2 bits for channel, 1 bit for DIMM and rank each. So, it is 2 plus 2, 4 plus 3, 7 plus 3, 10. Out of 36 bits, 10 bits are already been gone. Now, it is split up for rows and columns. So, how will you find out the number of rows and columns? The bank configuration is in such a way that the number of rows and columns per bank is equal. So, you have now 26 bits left. This is going to be divided across rows and columns and if you wanted an equal split up, then it is going to be 13 and 13. So, I have 13 bit for row and I have 13 bit for column per bank. That is the way how you divide. So, what is the total number of columns per bank? That is our first question. So, I have total of 2 power 13 columns are there. Now, what is the total number of rows in the entire DRAM system? So, if you look into the entire DRAM system, 13 bits are for column and 3 bits is for byte within the bus. So, total of 16 bits is been removed. So, I have total of 36 bits out of which 16 bits are already taken by byte in the bus and the column. So, I have remaining 20 bits and that many columns are there, meaning I have 2 power 20 rows. That is also equal to, if you take up the row bits, so for an easy conversion, if you take up the row bits, that is 13 and I have to add these 3, the next 1 each. So, it is 4 plus 3, 7. So, 13 plus 7 total of 20, meaning I have 2 power 20 rows. So, there are 2 ways in which I can use. First, you remove from the total address, you remove the column bits and the byte within the bus bits. Those are removed, then you have balance of 20. Or in a bank, I have 2 power 13 rows. I have 8 banks, so 2 power 13 into 2 power 3, that is 2 power 16. Then I have 1 bit for rank. So, I have 2 ranks, so into 2, I have 2 DIMMs, again into 2, I have 4 channels, again into 4. That will give you total of 2 power 20. Now, continuation of this question, if the system is using row interleaving in banking, which bank the physical address 0x844332255 is mapped? So, we have to understand what is meant by row interleaving. Row interleaving means adjacent rows are mapped onto adjacent banks. So, once all the column bits are over, then comes the bank bits. So, let us try to find out the scheme of the address. You have the last 3 bits that is going for the byte within this bus and then this is the bank bit. So, row interleaving means once the column bit is over, then you have to use, and this is what is called the remaining 4 bits. So, we have 13 plus 3, that is 26, 26 plus 6, 32 and this makes 36. This 4 corresponds to 2 bits for your channel, 1 bit for the DIMM and 1 bit for the rank. So, this is the split up. So, the main point in this context is once the column bits is over, between the row and the column the bank bits will come. That is what is known as row interleaving. So, row interleaving is a concept where adjacent rows are mapped onto adjacent banks. So, once all the possible bit values are given in the column, the next column number should be mapped into the next bank. So, that is the way how it works. So, we have to extract these bits. So, now let us try to take the values. So, the last, so 3, 2, 2, 5, 5, these are the last 20 bits, out of which 3 stands for 0, 0, 1, 1, 0, 0, 1, 0, again 0, 0, 1, 0, and this 5 is 0, 1, 0, 1, 0, 1, 0, 1. Now, this last 3 bits, this is going for the byte within this bus, and then I have 13 bits. So, this much is this 13 bits, that is the column. So, this corresponds to the column number, this corresponds to the byte number, and these 3 bits are going to tell you which is the bank. So, the value is 0, 1, 1, that means bank 3. So, this particular address correspond to third bank. Out of the 8 bank ranging from 0, 1, 2, 3 etc. up to 7, this corresponds to bank number 3. Now, the second portion of the question, we look into the second portion of the question. If the system uses 128 byte last level cache and is using cache block interleaving in banking, which bank the physical address is mapped to, which channel serves the data. So, the previous question also, which channel serves the data, we know that the most significant 2 bits is the channel. So, here the most significant 2 bits is, that is 8, 8 correspond to 1000. So, the most significant 2 bit is 1010 means 2, so it is corresponding to channel 2. That was the first case. Now, in this case, we will see what is cache block interleaving. Now, once you come to cache block interleaving, adjacent cache blocks are mapped onto adjacent banks. So, this is the address, last 3 bits. Now, since I am using 128 byte last level cache, 2 power 7 bytes will fit into my cache. Already in a single word 8 bytes have gone. So, 128 bytes has to fill in a cache. So, every 128 byte should be located in adjacent banks. So, I have 128 bytes of data that comes from main memory. The next 128 bytes should be kept in another bank, then only it is going to help us. So, if you wanted to get 128 bytes, then it is 2 power 7. So, the least significant 7 bits should constitute one cache block, and this is called the lower column address. Once this 7 bits is over, then we should have our bank bits. I have total of 13 bits required in the column. So, the column bits, 13 bits of column is being divided into lower column bits. This is what we have seen, that is column lower, and then we have column higher. So, how much will be there for column higher? Already I have 13 bits, out of which 4 bits is already taken in the column lower, and the remaining is 9. So, the idea is total of 13 bits is going to be divided into lower portion column and upper portion column, and in between the bank bits are inserted. So, I will summarize again. We have cache block interleaving, and in cache block interleaving, adjacent cache block data are mapped onto adjacent banks. In this case, we have 128 byte is the block size of the cache. So, from main memory, always 128 bytes of data are moving to the cache, because access to main memory comes whenever there is a last level cache miss. So, once 128 byte is gone, the next 128 byte is the next demand. So, rather than keeping adjacent cache blocks in the same bank, cache block interleaving means every cache block, every adjacent cache block is mapped onto adjacent banks. So once 128 byte is being transferred, the next 128 byte should be located in a different bank. For that to realize, to get 128 bytes, we require 7 bits. So consecutive 2 power 7 locations are being transferred, that is the last 7 bit, and then comes the bank bit. So my column address is not fully over. So what we do is, the entire column bits of 13, we have total of 2 power 13 columns, so 13 bits will represent a column number, that is going to be divided into lower portion of the column and upper portion of the column. Between that, the bank bit is introduced, and then we have this 13 bit of row and the 4 bit that constitute the channel, dim and the rank. Now if you write the address, it's 68AA. So if you write the 68AA into the decimal equivalent form, 6 correspond to 0110, 8 correspond to 1000, this A is 1010, again 1010. Now out of which the last 3 bits are gone for bank, or it's basically your bus values, that means byte within this bus. Next 4 bit is the lower order column bits. So this will be column bits, and then we have 3 bits for the bank. So this is essentially, so this side is for my columns balance. So these 3 bit value is 001, that means it is bank 1. So I have to find out these 3 bits in the address. So remove the last 7 bits and take the next 3 bits, and that is corresponding to your bank. So in this context, this address maps to bank 1. Now there is one more portion in the question, which channel serves this, and channel is the most significant 2 bits. So if you take 2, 0, 0, 1, 0, and the most significant 2 bits will tell it is channel 0. That's why it is being connected. So this is how you solve the problem, given an address, given the split up into ranks, banks, rows and columns. You find out the mapping of the address, which all bits constitute ranks and banks, and based upon the type of interleaving. If it is raw interleaving, after the column bits, the bank bits will come. If it is cache block interleaving, depending on the size of the cache block, that many bits has to be kept from the least significant side, and then you insert the bank bits. So that completes your third problem for this tutorial. Now this is a multiple choice question. In a DRAM system that follows open row buffer management policy, which of the following sequence of commands are generated if the new request is to a different row from the row that was accessed last? So what is the idea? We have a row buffer for every bank, and you transfer the contents from the row into the row buffer, and you apply column number and you extract the corresponding value, and that is being sent on. Now while doing this, when the next request is to the same row, then only column numbers are given, because it is an open row buffer management policy. If it is an open row buffer management policy, then after every access we keep the row buffer as it is, assuming that the next access is to an already opened row. Now the question tells that in a DRAM system that follows open row buffer management policy, open row buffer management policy means I leave the row buffer as it is, such that if the next request is to same row, there is no need to take the row again, already the row is open, just give the column address and take the address. If the new request is to a different row from the row that was accessed last, what are the commands that we have to give? You have to give activate command, precharge command, activate followed by precharge, or precharge followed by activate. Activate is a command which is used whenever a new row has to be brought into the row buffer. Precharge command is used whenever the contents of a row buffer has to be returned back to the row. So in this case, there is something in the row buffer that is not the row what I want for the new request. So first I have to write it back. So I have to do a precharging first, and then the new row has to be brought into the row buffer. So the correct answer is, it is actually an active and precharge followed by activate is the correct option. So, pre-charge will write the row back into the corresponding row, write the contents of the row buffer, and then activate means the new row is taken into the row buffer. Now, let us go to the another problem. For a sequence of memory requests coming to a particular bank at regular intervals such that every request reaches the scheduler when the processing of the previous request is in progress. So, already I am progressing, I am servicing the request. Now, while the service is in progress, new requests come to the queue. The meaning is, once one request is completely serviced, the queue has an element. If the queue has the same row which is already opened, then there is no need for any pre-charge or activate, I have to just enable column address drop. If it is to a different row, then I have to pre-charge it and then I have to again activate. Now, the options that is given, open page policy gives lesser average turnaround time than closed page policy. What is the difference between open page policy and closed page policy? In an open page policy, our assumption is the next request, the next incoming request will be there to the same row what is currently opened. So, I won't close it, I won't pre-charge it, I leave it open. And what is a closed page policy? Once I have completed servicing of a current request, if the queue is empty, then I close the row, I do the pre-charge. But if the queue is not empty, we come to know whether already opened row, can I service an incoming request. So, open page policy gives lesser turnaround time than closed page policy, that we cannot say, because in this case you are getting requests at regular intervals. Closed page policy gives lesser turnaround time, that also we cannot say. The peculiarity is, and closed row policy will differ from open row policy if and only if by the time I complete a memory request service, my queue should be empty. If the queue is empty, means there are no more pending requests, then closed row policy will close the page by using a pre-charge operation, open row policy will leave it open. If the queue is not empty, then either it may be to the same row or it may be to a different row. So, in that case, open row policy and closed row policy is never going to be different. So, both open row policy and closed row policy will give the same average turnaround time. That is the answer, because there is no difference at all. By the time you complete the request, the next request is already there. Whether it is open row or closed row, either you have to pre-charge and activate, or you have to give only the column address when there is a row hit or when there is a row conflict. So, this gives you a better idea about the difference between open row policy and closed row policy. So, with this we come to the end of today's tutorial session. We first worked on a problem with respect to virtual memory, finding out the size of the page table, and then we have 2-3 problems that were dealing with the address mapping in DRAM, finding out channels and bank numbers from a given address and a given constraint. And then we learned little bit about the significance of activate, pre-charge and column address strop commands. So, I think this will give you a fair background in working with address mapping techniques in DRAM. So, with this we complete this tutorial. Thank you.